Hello and welcome back, everyone. In this video, we're going to talk about control systems or a little bit of control of robots. Now, we already talked about sensors, actuators, and the power supply. And this is the part where we talk about the brain of the robot, which is a controller. I'm going to be talking about how do you mathematically solve all these things and how do any robotics student or any robotics engineer actually solve all these things in terms of maths. Okay, don't worry, since you are still on the introduction module, I'm not going to dive into maths directly. Rather, I'm going to talk about it. Okay. So, it's going to be more of the introduction to mathematics and understanding how this is being done. And yeah, I hope all of you, enjoy this, little book or video or little chapter actually of control systems. Okay. Let's dive into it then. Okay. Now we have the chapter 4 now, and let's move on to the next one. We'll talk about the control systems. Okay. So control systems are used to regulate the behavior of robots. They ensure the robots move and perform tasks in a safe and efficient manner. And that's kind of like very important for a robot. Okay. If the robot is not doing what it's supposed to do, then it's a problem. If it's creating problem, then it's a problem. So control systems are the one which decide upon, if the robots are doing good or not good. Okay. Control system use sensors, actuator, and feedback loops to adjust the robot behavior in response to changes in the environment. This is where our previous chapter comes into play. We understood that sensors are the one which understand the physical environment. Actuators are the one which make an actuation. And feedback loops are essentially a connection between the sensor and the actuator, which continuously updates and tells the controller what is happening and when. Okay. Now, this entire situation is basically what allows a robot to behave like a human being. Okay. Where you adapt to something, then you think about it, and then you act. Okay. So the same thing happens in a robot as well. You sense something, you think about it, and then you act. Okay. Then we'll look at type of controls in a robot system. Okay, we have two types of control, which one is an open loop and the second one is closed loop. Very important. Now, you might be in bachelor's, you might be in school, you might be in your master's, everywhere, or even a working professional as well. Everywhere you need to know this term that it's either going to be an open loop or a closed loop. Now, open or closed loop, irrespective, is going to allow you to understand that a robot or any robotic system is going to be either having a closed or an open loop. Okay, that is, and let's understand what is a closed loop and a open loop in a little bit. But let's talk about the open loop first. So open loop control system are simple and inexpensive. Okay, but do not provide a feedback to the robot. I'll tell you what I'm talking about. Let's say you and your mom are talking about, is it raining outside or not? Okay, there can be two situations. Okay, if your mom asks you, is it raining outside? Then you go out and check if it's raining, and then you come back and you tell your mom that it's raining. Okay. Second option could be that your mom asks, is it raining outside? You go out, check if it's raining, and don't tell your mom. Okay. Now, in an open loop and a closed loop, exact thing happens. You go out, you check if it's raining outside, but you don't tell your mom that it's raining outside. Okay. That's an open loop. A closed loop, however, is the one where you go outside, check if it's raining, tell your mom it's raining. Okay. The main idea over here is that the person or this point who asks for information, okay, asks obviously for you, but also for himself or herself as well. Okay. And a closed loop information is traveling in a closed path. Okay. In an open loop, it just goes one way. That's very important for you. Okay. In an open loop system, the robot performs a task based on predetermined set of instructions without any adjustment based on the robot behavior. Very straightforward. Okay, your mom told you to go out and check if it's raining. You checked. That's it. No feedback, no information to the controller or your mom. Essentially, in this case, that it's raining outside. Okay. A closed loop, however, is a system that is a more complex one. And it's expensive as well, but provides feedback to the robot. Okay. Let's look a little bit example. The robot behavior is consistently monitored and adjusted based on the feedback from the sensors. You go out, you check if there's raining outside, and then you come back and tell it's raining outside. Okay. This difference of open and closed loop allows for a robot to decide and be dependent or independent. Usually, all the robots which are autonomous robots have a closed loop system where they continuously keep on updating the information depending on the feedback from the sensors, and that's very important. Okay, now we are going to step up the game into kinematics. Okay, now this might be a little scary part for a lot of people who are afraid of maths, but don't worry. we are not having a lot of maths right now. We would have maths, but it's still going to be pretty easy. And I would try as my best possible to use tools which doesn't really require you a lot of extension or a lot of understanding of maths. Rather, you can use drag and drop tools, and that's going to make things quite easy for everyone. Okay. Now, kinematics is a study of motion without regards to the forces that cause the motion. Okay. In robotics, kinematics is used to analyze and control the movement of a robot. Now, kinematics in general, okay, it's basically a study of machines which allows you to, understand how a machine is working. Okay. It can be for, anywhere around, that, you are having a robot or you're having a different kind of machine altogether. And they are, working in an environment. Now, if you want to mathematically prove they are going to be just fine, you need to have a mathematical model which is going to represent those machines in a math equation. Okay. And then you can say, okay, this is something which is definitely going to work and it's not going to fail. Okay. If mathematically or kinematically it's working, then chances of it being accurate is quite high. Not absolutely high because it's still on paper. It's not in real life, but it's mathematically correct. Okay. And that's what kinematics tells us. Kinematics is important in robotics because it allows robots to improve and in a precise and controlled manner. Okay, if you want to make your robot move in a very precise based manner, you need kinematics. Otherwise, movement of the robot becomes very jittery, very slow, very laggy, and you don't want that, right? I mean, who wants a robot to be very slow and very laggy? And then kinematics analysis involves the use of mathematical models to describe the robot motion, such as position, velocity, and acceleration. Now, since you have everything in terms of an equation, you can analyze all these things and figure out the best possible path, the best possible acceleration, and the best possible motion for a robot. Okay. And that's going to give you an edge over the existing system. What you're doing is you're creating an environment where you can monitor and plan everything before the robot actually goes out into the market. And that's the beauty of it. Kinematics is divided into two parts: forward kinematics and in inverse kinematics. Okay, not reverse kinematics, inverse kinematics. So forward kinematics is basically when you start from the source and you tell the robot the position. Okay, I'll tell you what we're talking about. Let's read the definition first. Forward kinematics is a method for determining the position and orientation of the robot end effector based on the joint angle of the robot. Okay, I think I should switch to my. Okay, let's take the example of your arm. Okay, in your arm, if you want to, let's say, grab this phone, okay, this phone, you might be thinking, I have all these phones here. I keep on switching phones. So yeah, let's say you want to grab your phone with your arm. In that case, what do you want to do? You tell the position and the orientation of the phone, correct? And your hand automatically solves and reaches this phone, okay? You see what is happening in forward kinematics, the method for determining the position and orientation of the robot and effector based on joint angle of the robot, okay? What you do is you want to reach this phone, okay? So how do you reach this phone? You tell, okay, my hand needs to be straight like this, and then it needs to move like this, and then it can just go and pick it up, okay? So you tell how much angle that this is at, how much angle that this is at, and it will reach the phone, okay? And this is what happens in forward kinematics. You tell every angle, okay? So let's say my phone is over here, okay? My phone is over here, let's say, okay? But what I want to do is I want to grab this phone. So I say my arm bends 30 degree, okay, and then my hand twists 40 degree or 30 degree, and then it grips, okay, and then it has my phone. So what it is, like, I told every angle of every joint, okay, and that's how it figured out, okay, where it has to go. And that's what happens in a forward kinematics equation. So forward kinematics is used to plan and control the robot motion, such as moving the end effector to a specific location, okay. Then you have inverse kinematics. Inverse kinematics is a method for determining the joint angle of the robot mechanical structure based on the desired position and orientation of the robot. The inverse kinematics is used to plan control the robot motion, such as reaching an object. Okay, let's come back to our main guy. Now, you know that the phone is here, okay? And you need to make this arm reach this phone. What you do is you tell the coordinates of this phone, okay? Let's say this from X, from X, it's at 7. From Y, it's at, let's say, 5. And there is no Z. So we are just working in two-dimensional plane. In that case, we tell the position and the robot is automatically going to solve using maths and figure out where it has to be so that it can grip the position. Okay. Inverse kinematics is generally used in robotics in industrial cases where the robot can automatically figure out what and where it has to be. And that's what we say in inverse kinematics. Now, how is it even possible that you are able to do inverse and forward kinematics? It's because of this beautiful mathematical equation known as Jacobian. Jacobians are mathematical matrices used to describe the relationship between the robot joint velocities and the velocity of its end effector. In very simple and easy term, you need a relationship between your hand or the gripper, okay, and your angles, okay, how it's working. So if you have a mathematical equation or mathematical system which can talk between your hand position and your angles of the arm, you can figure out anything, any position in the world, because essentially either you tell where the hand should be, or either you tell how the arm should be. Okay, so the relation between both of these is known as Jacobians, and that's what solves all these equations. So Jacobians are important in robots because they allow the robot's motion to be controlled based on its end effector velocities. Okay. Now, velocity is a term which you will hear in robotics quite a lot. Okay. How fast your joints are moving and which direction is it moving. That's what joints speeds are determined with the help of Jacobians as well. Now, in conclusion, control systems are an essential component of robots which allows them to move, perform tasks in a safe and efficient manner. Okay. This might be a little bit an extra cherry on the top, but you might have understood by now that, robot needs a lot of control so that they can perform even simple basic tasks as well. Kinematics is a key aspect of control systems, providing the mathematical model necessary to analyze, control the robot motion. Okay, very straightforward. Forward kinematics, inverse kinematics, and Jacobians are important tools in kinematics and analysis, allowing robots to move in a precise control manner. Okay, again, very important and very straightforward. And we are done with the little bit of introduction to our controller chapter back. Okay. Now, I hope you have understood what I want to talk and what I want to say, that you need a control in robotics so that you reach the point where you want. And the way the robot works, is clearly dependent upon how your robot or how your system is programmed for. So, forward kinematics, inverse kinematics, Jacobians, all of these are quite an important topic. But I hope all of you have understood this, and I hope you're having fun so far. I'll see you in the next one. Till then, happy learning and peace.